Okay, schedule. It was mentioned before class about the next exam. The next exam is scheduled for Friday the 13th, and we will have the exam on Friday the 13th of next week. Yeah. So I will be lecturing today, finishing groundwater and talking about glaciers, and then probably starting a little bit into geologic time. On Monday, I'll lecture on geologic time. On Wednesday, we'll have a homework assignment due, and I'll be reviewing in class on Wednesday. Then we'll have an exam on Friday. So getting started. We've talked about groundwater, water that is below the surface. Now we're going to talk about surface water and drainage systems. So let's just get right into it. Running water is a big thing that causes the shaping of the Earth's surface. The shaping of the Earth's surface is primarily two things: running water and air action. I read an article yesterday about the Rift Valley there in Africa, saying that, well, the article's title was very provocative, that the ground just split open. Well, not really. It says later on, yes, it's going to take millions of years for this to happen, but the ground is splitting. So that is also something that shapes the surface of the Earth, is the rifting, the splitting, and the moving of the plates. But a lot of the Earth's surface features are governed by water. So we're going to learn about that. Now, this picture is going to show up again on another slide. Just so you know, I didn't make a mistake and put the same slide in twice. It's the same picture to illustrate the second time a little more detail. So streams, have you ever wondered why streams are not straight? No, it never crossed my mind. Well, in some cases, it's pretty clear. If you have a mountain with a bunch of rocks, the stream's bouncing from this rock over there, it's pretty clear it's going to move around because you had soil here and rock there. But if you have a pretty flat meadow, the streams are always curved. If you look at something like the border between Iowa and Nebraska, first let's just check our knowledge of the state that we're going to school in, if not living in. What delineates the border between Nebraska and Iowa? Yes, it's the Missouri River. So it's not a perfectly straight line. And in fact, have you guys flown out of Epley Airfield? Epley Airfield is in Nebraska. And just beyond it is the Missouri. And then right beside Epley Airport, you have, Carter Lake, Iowa. Carter Lake, Iowa, on this side of the Missouri River. Has anyone ever noticed that? No? It's really weird. There is a region on this side of the Missouri that is Iowa. And the reason is, as we'll see, when you have a heavy flow, like, flood condition, you can have the river change. And the river has changed. So the river used to come up there into Carter Lake. And when they set the boundary, that was Iowa because of the way the river was flowing. But then the river cut off, left that what we call an oxbow lake. And so there's that region there that's now on the west side of the Missouri River that used to be on the east side of the Missouri River. And so it's Iowa still, and it's kind of weird because you live in Iowa, but you're surrounded by Omaha, Nebraska, and you can't get to Iowa except for by driving through Omaha, Nebraska to get to a bridge. So we're going to learn more about this, so I'm not going to talk about the details of this until we come back to it. The drainage basins is something that makes sense logically, but you often don't think about. I remember crossing over the Continental Divide and thinking to myself, what is being divided here at the Continental Divide? Is this the midway point? Well, no, it's a little bit too far west to be the midway point. What the Continental Divide is a division of where water goes. You have water coming down from the sky. Today it happens to be frozen. That water, when it hits the ground, is going to drain somewhere. And so the Continental Divide is dividing where the water drains. if it's on the west side of the continental divide, it's going to drain into the Pacific Ocean. If it's on the east side of the continental divide, it's going to drain into the Atlantic Ocean. So we call those drainage basins. They're draining everything that is on the east side of that continental divide is draining into the Atlantic Ocean. So it's one huge drainage basin to get into the Atlantic Ocean. So that's what the continental divide is. It's if water falls here, it's going to go there. If it falls a foot over here, it's going to go there. In theory, of course, is it really a foot over? It's probably a little broader than a foot for the true continental divide. So anytime you cross over the continental divide now, you know what that means. It's going to go either, it says the Gulf or Atlantic Ocean or the Pacific Ocean. So, of course, where I grew up is all Pacific Ocean, pretty clear. And where we live now is all going to the Atlantic. Erosion and deposition are really important things that happens with flowing water. Erosion is transporting material. Deposition is dropping it out so that it adds to whatever is there. And water speed makes a huge difference to this process. First, laminar flow. Laminar is a word that means in layers. So laminar flow, the water is flowing in layers. Laminar flow is a smooth flow, and laminar flow does not carry a lot of sediment with it. But turbulent flow, which is exactly what the name says, turbulent, the water is doing this kind of action, and it will pick up stuff from the bottom and carry it. So turbulent flow carries a lot more stuff in the water than smooth laminar flow. And so I actually already pre-highlighted this as I was preparing for lecture. The laminar flow carries only the lightest particles. Anything that's heavier just gets dropped out. Turbulent flow can carry much heavier objects. If you have a really turbulent flow, you could be carrying rocks. And so when you have water flowing, you have that turbulent flow, you carry a lot of stuff. When the water smooths out, it'll start dropping it out. It'll start having sediment. That's how we move stuff, how nature moves stuff. Now, what causes things like this in rocks? You guys probably had a different childhood than I did. We spent, a week every summer up in fish camp just outside Yosemite. We still spend a weekend there because it's a family tradition. And you see lots of things like this in the rocks. When I was a kid, I always believed that all of those were carved out by Indians using that to grind their corn and stuff. Why did I believe that? Because that's what they show you in the Nature Center. What I didn't understand was that those things are natural features that the Indians then utilize because, hey, look, this is perfect for grinding it. Those are caused by a couple of different options. You can have chemical weathering. That is, you have a stream carrying substances that erode the rock just because of the chemistry reaction. For instance, that's, of course, most prevalent when you have a calcite or something like that will be, or limestone, that will be absorbed or dissolved by any acidic fluid. But you could have other things that cause chemical weathering as well. Hydraulic action is just the water is coming and swirling, and that swirling water is putting frictional forces on the rock and slowly breaking up a little bit of rock at a time. Or you could have abrasion. You could have like pebbles that are swirling around in there with the water, and those pebbles would do a whole lot more abrasion than just the water itself. And so when you see things like this, or the smaller ones, they're just little divots that are nice and smooth, those are signs that the water has worked it out and eroded it. Now, stream erosion, which is what I usually consider a big thing, is done by higher energy, stronger currents, and creates things like this. I am pretty sure I know where this is. Where do you guys think this is? Yeah, that's where I believe it is too. I believe this is Yellowstone. And I can't remember the name of the waterfall there, but I remember hiking down to it. So when you have water flowing through a valley, it tends to form a V shape for the walls of the valley. So this is a classic example where you see a V shape. It's pretty much straight lines coming down the slopes. So that's one of the important things to keep in mind. When you see a V-shaped valley, you can say with a fair degree of certainty, this valley was probably caused by a stream flowing through and over time causing erosion. And so just think about how much time it's going to take to carve in that much. It's going to take a really long time. That's one of the reasons why geologists believe in a very long time scale, because if things go at the present rate, it's going to take a very large time. Now, creationists will counter and say, what if the flow rate is faster? What have we learned about flow rate and carrying stuff? If it's flowing faster, does it carry more or less? It's going to carry more sediment. If you have it flowing faster, it's going to cause more erosion. And so the erosion could be much, much faster if the water flows really fast. So creationists say, no, that's probably not a lot of time. It's probably an enormous amount of water for a shorter period of time. So you have two different ways that people will interpret what you see here. The standard scientific interpretation is it took a very long time with somewhat similar flow for that time. I say somewhat similar. Certainly, standard science says it's possible for you to have times of faster flow. Now getting back to the same picture and talking about it more carefully. When I have a bend in a creek, the water has to change direction. And so that means the water going straight is going to go until the boundary, the bank of the creek, causes it to turn. And so the water is going to come and push on the side here and erode away. So it's going to erode more and more there at the turn, which has as its effect making the turn become steeper and steeper. On the other side, so on the inside of the curve, the water is not brushing up against that really. It's moving away from it. It slows down, and because it slows down, it starts depositing. So you have deposition on the inside of a curve and erosion on the outside of a curve. So that's going to make a curve in your creek bigger and bigger and bigger. So to start this curve, all you really have to do is there's a rock here. The rock makes the water deviate over there, causes a little more erosion there. Now I have a curve. But now because of that curve, it's going to erode more and more, and it becomes a bigger and bigger and bigger curve. So the position of the stream, if you have a flat region, what we call a floodplain, it will move. We say meander across the floodplain being the smooth region. So if you start with, here is a flat area, right? Okay, I wrote flat, and of course that's a bad place to do it because that's where we want to look at it carefully. So in this flat region, the stream comes down here and it's cutting its arc, or its path. But because of the action we've just talked about, this point here will slowly move out, this point here will slowly move out as it erodes in. And it will leave behind filled in areas. And so over time, that same region where it was flat becomes a bigger, flatter valley, right? This is definitely flatter than you had up in the first picture because the stream has extended across and then it just deposits behind it, filling in at roughly the same height. So this kind of stream, by the way, is called a meander because it meanders across the floodplain. And now the thing that makes Carter Lake. Carter Lake is a lake, but it is a lake like this. It's an arc-shaped lake. Why is it an arc-shaped lake? Because the Missouri River used to come out and go like this, and then with the storm, it cut off and left that part of the river as just an abandoned piece of river. So it's still pretty big, right? The Missouri River is not some small river. It's still pretty big, but it no longer has water flowing in and flowing out. Those have been cut off. And so you're left with the trapped water area. That's what we call an oxbow lake. So Carter Lake is an oxbow lake. Let's actually, I've mentioned Carter Lake enough in today's lecture. Let's go look at Carter Lake just to Carter Lake, Iowa. Here's an overhead picture of Carter Lake. That'll be good. Really? That's okay. I thought that would be good clicking on it, but it's not what I wanted. This simple Google map will show us what we need to see. The lake used to go, oh yes, can't write on this. The lake used to go like this. How do I know? I'm just following the boundary for Iowa, Nebraska, right? Since the boundary was based on where the lake or where the river was. So you just go like this, come around, and come back like this and continue on. But in a time when you have very heavy flow, you're going to have a whole lot of force pushing here, and it just dug a new trench that was cutting off all of that extra distance it would have to go and filled in, separating that region. So that's how the Oxbow Lake was created. And so you see Epley Airfield here is right there in the region where it was cut off. Question?
So the only question I have is, you know that water got trapped there?
Mm-hmm.
What closed off the rest of the water from just like sliding down? You know what I mean?
You mean from filling back in?
Yeah.
From that? That's once the water had punched its new pathway, it's depositing on the sides, and so sediment from the river plugs up.
Oh, okay. Because I was gonna say, how come like the flow on that one didn't just continue going down?
Yeah, a reasonable question. And it's, you had water flowing there, you punch this new path. Initially, you probably have some water that's going in there still replenishing it while the new path is coming out and building up more and more borders until it gets trapped. Back to this. Come on. Well, right now things are crashing. Okay. At least it didn't completely quit, which it often does do. So that's a meander in a floodplain. So here you have roughly an equal level all across the plain where the lake is, where the river is meandering. And so that region where the river is meandering back and forth, that is the floodplain. And you can see how it builds natural levees, the deep channel. And over time, the stream has been over here where this was the boundary and the stream was like that, or over here where the boundary was like that. And it'll move back and forth. So anytime I look at a stream and I see it going through a flat valley, now I say like, oh, that's a meander. To me, that's something meaningful. Now, deltas I've talked about in the past. Deltas is what occurs when you have a fast-flowing river meeting a non-flowing body of water. You go from a fast flow carrying lots of material to a slow flow where it all falls out. And so you have lots and lots of sedimentation occurring there. And so this here is all sediment that's been put on top of the original ocean floor. And so it's fan-shaped, which is where they get the name delta, because it looks kind of like the Greek letter delta. So 2 clicker questions with the same options. This picture shows an example of what geologic feature? Yes, that is an airplane. I was looking at the picture earlier and I was like, what is that in the middle of the picture? First I thought it was something on the ground, but yeah, it's an airplane. Waiting for Ivy and Leslie.
Sorry, my thing is in a different channel. Oh, I didn't go through?
No.
Oh.
Okay. Okay, so our answers were 4, 1, 1, 0. Okay, we don't have enough information to see if there's turbulent flow or not, but a meandering stream is rarely turbulent flow. It's usually fairly smooth flow. Where do deltas occur? I just can't hear.
Oh, where the flowing water meets the standing water.
Where the flowing water meets the standing water. So is there flowing water hitting standing water here? No. So it's not a delta because there's not flowing water hitting standing water. We certainly would not expect to see rapids here. It's probably not turbulent. It definitely is a floodplain. Now, if you look here, can you see features of oxbow lakes anywhere? You can see the lake the river used to go like this. Okay, the blue's probably not standing out enough, but orange. Ooh, the highlighter. Nope. Highlighter was a bad choice. Back to orange. It used to go like that, but it punched through a long time ago. How do I know it was a long time ago? Because now it's going the opposite direction completely. And assumedly it punched through like this and then it worked its way across. So you have there a sign showing you that it's changed its path. I'm sure there are other places. It's kind of hard to tell the difference between a road and other places where that might have occurred. Next time you get a big rain, you can be pretty certain something's going to happen right here. Right? What's almost certainly going to happen next time you have a big rain here? On the picture here we see right now, next time you have a big rain, so a heavy flow down the river. Yeah, almost certainly it's going to cut across right here. Now, how is it going to end up? Will it be exactly like that? Will it be like this? I don't know. But almost certainly it's going to cut across there. It's, the erosion is so close to eroding through right here already. So that is not long going to remain. And you can look at this and see other places where, if you have a good flow, there's a good chance that this is going to start going like this and get down and cut that off, and so on. Okay, next clicker question. This picture shows an example of what geologic feature? And it's the same exact options. Come on. Okay, well, hit that button twice. Okay, now it's open. By the way, this here is ocean up here in black. This is land that's kind of yellowish. And the green is, well, pretty clear. Okay, still didn't record you, Ivy.
Did it?
No. Aren't you glad I tell you rather than just say, well, there goes your grade? Okay, 5 people went with delta. That's the correct answer. This fan here, now if it was the letter delta, it would go across like that. Need to change. The letter delta would look like that. Obviously, it's not a perfect delta, but that fan shape is what we call a delta. So you're seeing a delta here. One person said rapids. With this kind of information, you can't tell if there's rapids. What's a rapids? That's where the water is moving rapidly. That it moves rapidly because you have a fairly rapid change in elevation, which makes the water flow faster. And then if you have rocks or something, it'll cause it to be very turbulent. So rapids are an example of turbulent flow. So this here, I think that this is, well, I shouldn't guess. Yeah, I just won't guess in which delta it is. There are some famous deltas, the Nile Delta, or the delta where the Mississippi hits the ocean. And I'm just not going to guess which one it is. Glaciers. Do we have glaciers today? Yes or no? Do glaciers exist today? Yes. Yes, they do. Has anybody been to a glacier? Ivy, you've been to one?
No.
Oh. Okay, I've been to a few glaciers. It wasn't until I graduated from college. Well, actually, it was when I started teaching. I spent that summer acting in Alaska. It was my first experience actually seeing a glacier. So when I was your age, I hadn't seen a glacier either. But glaciers are places where you have ice that does not melt during the summer, it lasts year round. That's what the definition is for a glacier. You have ice year round. And those glaciers, you have 2 fundamental types. You have alpine glaciers. Those are ones in mountains. And continental glaciers, well, continental glaciers would be ones like Antarctica, where you have a glacier that's just covering the continent there. Glaciers accumulate ice from snowfall. Snow falls, it gets compressed under the weight of more snow above it and compresses to form ice. Now, in that process, you have snowfall. There's going to be lots of air between the snowflakes. By the way, it stopped snowing now. There's going to be lots of air between those snowflakes. You start compressing it, what happens to that air? Okay, it's either going to have to squeeze out or be locked in and compressed. Both of those are going to happen. So if you take a piece of glacier ice and you look at it, if you look at it from the side, it looks like nice, clear ice. But if you look at it from the top, you see lots and lots of little bubbles. How is it that you see bubbles when you look from the top and no bubbles when you look from the side? The trapped air pockets have been flattened because of more and more pressure. And so you have those trapped air pockets. One of the things that scientists do when they study glaciers is they check out the composition of the air that's trapped in those little pockets to tell them about what the atmosphere was like when the snow fell that made that part of the glacier. So scientists will drill bores where they drill a bore and keep the center part and study the ice at different depths to learn about what it used to be like where the ice was formed. Now, glaciers, like alpine glaciers, they're usually moving. You can have glaciers that don't move. Continental glaciers are pretty much fixed. They're not sliding around. But alpine glaciers are usually sliding down. And so as they move, you're going to have a lot of changing of the earth. Because if you have a big, huge block of ice that's miles long, sliding, it's going to grind up a lot of stuff. So here's a picture illustrating what's happening when you have a glacier flowing. So when it becomes 50 meters thick, how much is 50 meters? Any sense of what that is? A meter is close to a yard, right? A meter is a few inches longer than a yard. So basically 50 meters would be half a football field, or roughly the width of a football field. So when the ice is that deep, it'll be deep enough that gravity can cause it to start deforming plastically. Plastically means it's permanently deforming. And so as it slides, this is showing motion of a glacier, and you had this much motion between the rock under the glacier and the ice. So maybe in this picture, it slid 5 feet on the ice. But the ice itself is also flowing. It's deforming. That's what flowing is. So the ice is flowed, and if you look here, the flow of the ice, if that was, what did I say, 5 feet? That'd be more like 25 feet that the ice itself has flowed. So something on the top that you use to measure would show the 5 feet that it's slid on the ground plus the 25 feet that the ice is deformed, and say, wow, it slid 30 feet. So on the top, you say it slid 30 feet. If you're looking on the bottom, it's only actually slid 5 feet, but the top layer has moved 30 feet. And so this dashed line is showing how much it's moved at different depths. Why are there cracks shown on the top here? Well, if you have the ice flowing, you have the ice is, compressing, stretching as it flows. And so that's going to make it break where it can break on the surface. And so those fissures are caused because of the deformation that's going on. And so you have lots of cracks in the ice because of where it slipped and where it hasn't slipped. Now, the ice, the glacier accumulates ice where you have snowing. This picture it's supposed to be a very large region. So at the top, you have mountains and you have snowfall coming down. That snowfall is adding to the amount of ice in the glacier. So the glacier is growing where you have snowfall. It slides down, and at the end, you have calving where pieces of the glacier are breaking off when it gets to water. That's what calving is. But in between, the glacier doesn't conserve its ice. You have what's called sublimation, where ice is going into the atmosphere, becoming vaporized water. Sublimation means it's not stopping at liquid. It's going straight from ice to vapor. There is one more thing that's not shown here. You will have some melting as well. So very often in the glacier, you will have streams that are flowing through the glacier. You have water that's going like this through the glacier. Sometimes it's in the middle of ice all around it with water just going through a hole in the ice. And sometimes it'll be down in the bottom where it's basically a stream between the glacier and the ice. So all of the grinding of the glacier sliding is going to move a lot of debris, a lot of material. The streams flowing will also move material. So here is a glacier valley. Now, if you look at this, the first time I saw a glacier, it was the Mendenhall Glacier up in Juneau, Alaska. And that Mendenhall Glacier, I looked at it and I thought, wow, somebody was smart and they put a road on that glacier to drive. Well, of course, I was very, very wrong. What in the world is all of this stuff here? It's not somebody's road. Do you suppose that's ice? Yes? You seen black ice before?
Yeah.
But what we call black ice is ice that you don't see. They say it's black, but it's not really black. It's just you don't see it. It's just a thin layer on the road. I can see that was a tricky question to ask because, well, yeah, I've heard of black ice. I've slid on it before. You know, what that is dirt and rock that's been ground up from the edges of the glacier. Where the edge of the glacier is rubbing against the mountainside, it's grinding up rock. And that ground up rock gets turned up on the top of the glacier. But of course, what part of the glacier should that turned up rock be at? If it's grinding on the edges, where are you going to find that turned up rock? Let's go back to this. We grind it up at the edges. So where is it going to exist? At the edges, yes. But that's not the edge, that's the middle of the glacier. Well, you can see where I drew my thing where it's grinding up here, but then we had this glacier met this glacier. The two glaciers merged together. And so now this used to be the edge of the glacier, now it's in the center. And you can see this one here is another place where two glaciers came in together. And so these here are showing where we had glaciers that flowed together. Now this stuff is called moraine. I think that's how it's spelled. We'll see in the next slide, and if I'm wrong, you can just laugh at me. It's called moraines. The moraine is the debris that's being carried, in this case, on the top of the glacier. It's an edge moraine technically, but obviously that's not the edge anymore. Now this valley, if you look at the shape of the valley, all you see is this amount. And you're like, well, what's the shape going to be underneath? Well, here's the shape underneath. Glacier valleys tend to be very U-shaped. U-shaped because you have this ice thing that's flowing down the valley, scraping out everywhere it's touching. Right? The water was only going down essentially the center, eroding where the water is. And for the glacier, it's scraping everything. It's flowing down the entire region, scraping all sides. And so the glacier gives you a U-shaped valley, whereas streams give you a V-shaped valley. So if you go and look at a valley, you can make a quick judgment. Looking at the shape of the valley, is it V-shaped or U-shaped? If it's V-shaped, it was probably formed by which type of moisture? V-shaped is formed by water. U-shaped would be formed by a glacier. And by the way, I had to put in this picture because it's my very, very happy place. Just in case you don't recognize things, that there is Half Dome. Amy had never been there, so I had to take her there right after we got married so she could see the place I love. Because it's important. What does it look like at the end of a glacier? Right now, we have lots and lots of glaciers that are receding. What does it mean for glaciers to be receding? Well, it means that the end of the glacier is moving back up toward the mountains. How can that happen? Well, we talked about the sublimation, the losing moisture into the air from the ice. We also talked about water flowing. You have some melting going on. And so those are causing the glacier to become less and less. If you have less ice being deposited at the top, then you're losing to those things. Then the glacier over time will slowly move back because there's not as much coming in as going out. Yes, ladies.
This is like a weird question, but was that ice age a real, like, actual thing that happened here?
Okay.
Wouldn't that be like glaciers too?
The best that we know of is, yes, we have had multiple ice ages. Multiple ice ages. We're still recovering from an ice age. The Earth's global temperature right now is right about the average temperature for, I think, the Pleistocene. It's been colder in recent history. There was a time, it's called the Maunder minimum for the sun. The sun was not producing as much radiation. If the sun's not producing as much radiation, it gets colder on Earth. And so during that time period, like the River Thames would freeze over, they'd have ice skating parties on it. And global temperatures dropped. And global temperatures have been rising because, well, we haven't had that situation. But we're still basically recovering. We still have lots of glaciers. And so some people will say we're still in the ice age. Some will say we're recovering. But yeah, ice age doesn't mean the entire Earth is covered with ice. But
Was it only certain areas then?
yeah,
Oh.
but pretty much most of North America, we believe, is covered with glaciers.
Oh.
Then we had glaciers, if you go up to Minnesota, the land of 10,000 lakes. Why does it have 10,000 lakes? Because of what's been left behind by glaciers. The glaciers cause a lot of small lakes to form. You see things like this. And so that's a primary feature when you look up there in Minnesota's landscape. You see things like this here is a terminal moraine. I showed you moraine that was coming down the middle of the glacier. Actually, it was from the edges and it joined. Well, at the end of the glacier, where the glacier stops, all of the moraine that's been carried by the glacier doesn't get carried any farther. And so it's starting to leave stuff as it comes back. And so at the end, the furthest point it advanced, it was like a bulldozer scraping stuff down. Then it backs off and leaves some stuff. And so you have the terminal moraine here. You have this esker here is the result of a stream that was running under the glacier. You have these drumlins, different features that are formed by glaciers that you see in the landscape up there in Minnesota. Anyone here from Minnesota? No. Okay, one.
Michigan has more lakes than Minnesota.
Oh, okay. So show some pride.
It drives me nuts because they call Minnesota the land of 10,000 lakes, but Michigan has over 11,000, not including the Great Lakes.
Although one Great Lake is equal to all of the others combined. I appreciate you defending your state.
Well, we have the Great Lakes was formed by lakes, but there's a specific, which one is the little lake that's formed by the glacier that the esker runs into?
These Kettle Lakes here.
Yeah, those, Lake St. Clair in Detroit.
Susie? Actually, Susie here is a pro. Dr. Susie Phillips from Loma Linda. She is here because she's an alumna of Union College. And as you can see, I have all ladies today. There is one gentleman in the class, but they're education majors. So they're not likely to come to you, but you can still.
No, but I still want to take the opportunity to tell you a little bit about getting a PhD, but only if you're.
No, it's fine. I only had
Oh, go ahead, but.
3 more slides, and then I was going to
Go ahead and
shift
finish.
off. Well, okay. That's it for the work of water in changing the surface of the earth. The last thing we're going to talk about in changing the surface of the earth is the effects of air. Air moves material. And, we see that out here in Nebraska. When it gets breezy, we get a lot of crud in the air. Well, you see this effect the most if you have sand. Because if you have sand, the air flowing, just like water, it will carry material in the air. The faster the air, the more material is probably going to be carrying. And then when it slows down, it drops it out. So if you have air flowing over sand, it flows up over the top, and then on the backside, the air tumbles down here, drops its load. Note it says wind shadow because the wind is not continuing fast in that region. And so you build up more and more in the backside of your dip. So that's how sand dunes actually form. And this pattern is seen not just in sand, but also in water. So you can have features underwater that show the same type of action and cause pretty significant changes to the environment. Now, people like those that Susie at least is boss over, examine sand deposits in sandstone, and they look for signs to say, was this a deposition caused by water flowing or by air flowing? And there's differences that they can tell. One thing is you always can tell the direction of flow by how steep it is. It's flatter on the side that the fluid, whether it's air or water, was coming from, steeper on the backside. But they can also tell just the slight variations if it was water environment, fluvial, or if it was an air environment. Was that alluvial? Aeolian, okay. And that helps them to better identify what they're looking at when they're looking at the sediments in lab. And so, clicker question, our last one. There are many erosive agents that sculpt Earth's surface. Which erosive agent does the most work? It says 6 people already responded, which clearly is not true. Well, that's wonderful. Okay, it's open now. Not sure why it said you all responded and closed, but say love you. All right. We have no clear consensus. So we had nobody said wind. One person said groundwater. 2 said running water, and 3 said glaciers. Let's put it on the pro. Which would you have answered? She would have answered C. She would have answered glaciers.
No, C. Running
Oh, C, running water. I can read. Running water. This is, I'm sure there is a correct answer, but it's something to think about just how much is each one of these doing. Glaciers are still covering a reasonable percent of the earth, and they're doing a lot of work still. Not nearly as much as in the past. Running water is obviously doing a lot of work right now. Groundwater does some. We talked about the sinkholes. Well, sinkholes are going to be caused by groundwater. It's probably running. But when it says running water, it means surface. Wind is causing changes. If you're in the Sahara Desert, you're probably going to say wind, because in that region, that's the primary one.